The International Mathematical Olympiad has been called the hardest maths competition in the world, but one of the beautiful things about it is that the problems are designed to be able to be solved using only high school level maths. That idea was the inspiration for this video, which I made a few years ago for the 3 Blue 1 Brown Summer of Math contest. The main character, Socrates, shows that even an uneducated slave can solve an IMO problem just by being willing to ask questions, use logic, and have the patience and persistence to see the process through. I hope you enjoy it.
Young boy, have you been trained in the ways of Olympiad mathematics?
No, Socrates, I'm just a slave.
As I expected. And yet, even you can solve Olympiad mathematics problems. Because in truth, your immortal soul possesses all knowledge, and you can recollect this knowledge through investigation and inquiry.
No, I don't think I can, Socrates.
You can. You can, and you will.
But Socrates,
Silence. Let us begin. I will explain the problem. Here we have 8 coins, 4 aluminium and 4 bronze. I will arrange them in a row. Then you should select the 4th coin together with all adjacent coins of the same type and move them to the left end of the row.
Okay, 3 bronze coins.
Then we repeat this process.
3 aluminium now.
Right, we move them to the left end of the row.
Okay.
And we keep on repeating this process.
Now those 4 bronze coins are already at the left.
Yes, the leftmost 4 coins all have the same type. Now our problem is to consider all possible values of n. And instead of just the 4th position, we may consider any position k. And we must find all pairs n and k for which the leftmost n coins will all have the same type for any initial ordering of coins.
I'm confused.
Okay, let's take another example, say n equals 5 and k equals 3. Please arrange the coins.
Okay, 3rd coin to the left. Now these 2 coins to the left. This time 3 aluminium coins get stuck on the left end of the row and cannot move.
The leftmost 5 coins do not become the same type. You have shown that n equals 5, k equals 3 cannot be a solution. And what would you say about n equals 5, k equals 4?
It cannot be a solution. I would place the 4 aluminium coins on the end of the row and separate the other one.
And if I were to give you 100 of each type and ask about k equals 99?
Again, it would not be a solution. I would place 99 aluminium coins, 99 bronze, and the last aluminium and bronze. Again, the sequence would never change.
So would you say that you have proved without a doubt that for the pair n, k to be a solution, the k value must be at least as large as n?
Certainly.
Well done, boy.
I feel quite proud of myself.
Yes, but recall that our problem is to find pairs that are solutions. And although we have ruled out some pairs, we have not yet found any definite solution.
Except n equals 4, k equals 4. We did that at the start.
Although we demonstrated one arrangement for n equals 4, k equals 4, we did not prove that it works for any initial arrangement of coins.
I see. I'll try something else. Worked again. I believe, Socrates, that it will work for any arrangement, and n equals 4, k equals 4 is a solution.
Can you explain why?
The chains keep on combining, getting longer and longer until there were only 2 chains remaining, 1 aluminium and 1 bronze.
A reasonable explanation, boy. Let's see if you can make it a little more rigorous. In each move, does the chain that moves always join with another to become longer?
Sometimes the chain that moves joins another like coin to become longer, but sometimes it does not.
Yes. And what about the other chains in the row?
The others? Oh, the coins to the left and the right of the removed chain always combine to form a longer chain.
And can you explain why this must occur?
Well, the 2 surrounding coins must be the same type, the opposite type to the removed chain.
Correct. Now tell me, with any move, can any existing chain break into smaller chains?
We always remove an entire chain and move it to the end, so no, an existing chain can never break into multiple smaller chains.
Right. And as no existing chain can break into smaller chains, but 2 chains must combine to form a longer chain.
I see. In the end, all the chains must combine to form 2 chains, 1 aluminium and 1 bronze.
Right. And when n equals 4, the removed chain must have at least 1 coin to its left and right because if the chain extended from the 4th position to the end, the leftmost 4 coins would already be the same. Exactly. And the same will apply whenever n is equal to k. And what would you say of the case where k is equal to n plus 1?
It must also give a solution. Similar to above, if the chain extended to the right end of the row, the leftmost n coins would be the same already.
So, do you think that all values of k larger than n give solutions to the problem?
Let me try another example. Okay, n equals 6, k equals 8 works because although there could be a chain extending to the right end, not all chains can. So the total number of chains must still keep reducing until there are only 2. And the same should apply for n equals 6, k is equal to 9, because a chain would require 4 coins from the 9th position to reach the end, which would leave a shorter chain of 2 coins in the middle somewhere.
Your logic is sound, boy.
But for n equals 6, k equals 10, the coins could be arranged in chains of length 3 like this. Every chain removed would extend to the end of the row, so the number of chains would never reduce.
Yes. Are you ready to state the solution to our problem?
I think so. K should be at least as large as n, but no larger than 3/2 of n.
That is correct. In some cases. But may I suggest you check a case for which the value of n is odd?
Okay, let me try n equals 5. 3/2 of n would be 7.5. Oh, but actually n is equal to 5, k is 8 would also give a solution, because chains of at least 3 would be required to extend to the end of the row. So for odd n, the k must be less than 1 above 3/2 of n.
You are correct, boy. Algebraically, we could express the distance from the kth position to the end of the row in terms of n and k, require that it be greater than half of n. This gives the upper bound as you stated, which applies for even or odd n. Well done, my boy. You have shown the people of YouTube that, although Olympiad mathematics is difficult, anyone with the capability to reason and communicate is able to solve such problems, if they are willing to persevere and investigate until the end.
Anyone with a wise and patient teacher, Socrates. Thank you.